Today, we will be exploring the solubility of a gas in water. To review an earlier unit, solubility is defined as a property of a chemical substance called solute to dissolve in a solvent. Throughout the course, we learned that the equilibrium constant for the equilibrium established between a solid solute and its ions in a saturated solution can be represented by Ksp, the solubility product constant. Ksp represents what level a solute dissolves in a solution. A higher Ksp value signifies a higher solubility. A solute's molar solubility can also be obtained from the inverse of the following reaction from the Ksp value. It should be noted that solids are not included when calculating equilibrium constant expressions because their concentrations do not change the expression. Any change in their concentrations are insignificant and therefore omitted. Even for very soluble substances, there is usually a limit to how much a solute can dissolve in a given quantity of solvent. Certain limitations and exceptions to solubility were outlined throughout the course. The first example is the common ion effect. In the event that there was a saturated solution of PbI2 and a common ion, being iodine, was added in the form of Ki aqueous, Le Chatelier's principle states that when the concentration of one of its reactants is increased, equilibrium is shifted in the direction in which that reactant is consumed. The addition of common ions shifts equilibrium towards the undissolved compound, causing precipitations, and the solubility of the compound is reduced. The second example is the limitations of Ksp constant. Ksp operates under the pretenses it is based on ion activities rather than concentrations. Ksp values are usually limited to slightly soluble solutes. The third example is the salt effect. In comparison to the common ion effect, the presence of non-common ions tends to increase solubility. This is because higher concentrations must appear in the solution before equilibrium is established. The last example is the incomplete dissociation of solute into ions. Some ions in solution might join into oppositely charged ion pairs. Additional solute must be present for the product ion concentrations to equal Ksp, making the solubility greater than otherwise expected. Throughout the Chemistry 112 lessons, we mostly focused on solubility when it comes to solids and liquid solutes. When it comes to gases, solubility decreases as temperature increases. The most physical reason behind this is that when most gases dissolve in solution, the process is exothermic. Heat is released and gas dissolves. This effect is very similar to the reason that vapor pressures increase with temperature. Increased temperature causes an increase in kinetic energy. The higher kinetic energy causes more motion in the gas molecules, which break intermolecular bonds and escape from solution. The most common example, which relates to our everyday life, is soda. Take a SodaStream machine, for example. CO2 is pumped directly into water. All carbonated beverages are bottled under pressure to increase the carbon dioxide dissolved in solution. Carbon dioxide can dissolve in water because CO2 is a polar molecule, as is the solvent water. When the bottle is opened, the pressure above the solution decreases and the carbon dioxide bubbles off. This is the reason that sealed pop cans stay fizzy over time. The equation for this phenomenon is CO2 plus H2O moves forward to produce H2CO3. We can also note that when the bottle is sealed, the system is in equilibrium as the forward and reverse reactions are taking place. The solubility of a gas increases with an increase in temperature. The solubility of a gas in a liquid is directly proportional to the pressure of that gas above the solution. If the pressure is increased, the gas molecules are forced into the solution since this will best relieve the pressure that has been applied. Gas and temperature can be related through the pressure law, which states that for a constant volume of gas in a sealed container, the temperature of the gas is directly proportional to its pressure. When the temperature of a system goes up, the pressure goes up and vice versa. This relationship between pressure and temperature of a gas is stated by Gay-Lussac's law. Throughout the first semester, we had the opportunity to explore gas laws such as PV equals nRT, which relate the pressure, volume, and temperature of a gas. Henry's law is another gas law that we have not yet learned about. It explains that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressures of the gas above the liquid. Thus, it can be drawn that the initial solubility over the final solubility is equal to the initial pressure over the final pressure. The law is also represented by the equation C is equal to Kp. C is the concentration of a dissolved gas, or also the solubility. K represents the Henry's law constant, which can vary from substance to substance, and P represents that partial pressure of the gas. Henry's law can be applied in different forms according to the conditions. In terms of the soda example we just reviewed, we can now think of it in terms of Henry's law applications. When a soda is still sealed, the gas above the drink is almost pure carbon dioxide, with the pressure being slightly higher than atmospheric pressure. The liquid itself in the sealed container also contains dissolved CO2. When the bottle is opened, some of the gas escapes, which can be heard as a hiss as the pop is pushed open or a cap is twisted on a bottle. Because the pressure above the liquid has now lowered to atmospheric pressure, the dissolved gas comes out of solution in bubbles, and over time, the drink becomes flat. Here is an example we can look at. Knowing the solubility of carbon dioxide is proportional to the pressure of the gas above the liquid, there is the scenario of Lisa. Lisa just bought a pack of her favorite soda, Orange Crush. If 0.24 grams of carbon dioxide dissolves in 1 liter of the liquid sealed under pressure of 2.5 atmospheres, what will the solubility of the gas be when one of the cans is opened and exposed to standard atmospheric pressure? We know standard atmospheric pressure is lower than the initial pressure, with the value being 1 atmosphere. After solving the algebra, when the can is open, the solubility of carbon dioxide in the soda becomes 0.096 grams per liter, much lower than the initial conditions of a sealed can. This examples prove why companies seal pop cans under higher pressures to increase the solubility of CO2 in pop cans and how it decreases over time. Scuba divers must also accommodate the solubility of a gas when doing deep-sea dives. Deep-sea divers may experience a condition called the bends if they do not readjust slowly to the lower pressure at the surface. As a result of breathing compressed air and being subjected to high pressures caused by water depth, the solubility of atmospheric gases increases in the blood. This is problematic due to the amount of dissolved nitrogen in the blood and other tissues that increase. If the diver returns to the surface too rapidly, the nitrogen forms bubbles in the blood as it becomes less soluble due to a decrease in pressure. The nitrogen bubbles can cause great pain and possibly lead to death. To avoid the occurrence of bends and the toxic effects of high concentrations of nitrogen in the blood, the tanks used by scuba divers are filled with air diluted by helium. The main reason for adding helium to the breathing mix is to reduce the proportions of nitrogen and oxygen below those of air, to allow the gas mix to be breathed safely on deep dives. Because of its low molecular weight, helium enters and leaves tissues more rapidly than nitrogen, and as the pressure is increased or reduced. With a mixture of the three gases, it is possible to create mixes suitable for different depths or purposes by adjusting the proportions of each gas. To solidify our understanding of Henry's law, here is another sample problem using the bends phenomenon. A diver begins at the surface of the water. Given the information that the aqueous solubility of nitrogen gas at 10 degrees Celsius is 11.5 milliliters of nitrogen gas per liter and 1 atmosphere, determine the new solubility when the diver swims 50 meters underwater to a new pressure of 5 atmospheres. First, we must solve for Henry's law constant for nitrogen gas. K is equal to the solubility over the pressure of the gas. We can then substitute the K value with the adjusted pressure value to solve for the new solubility at the lower depth. Solubility is equal to pressure over Henry's law constant. After solving for the algebra, the new solubility is found to be 57.5 milliliters of nitrogen gas per liter. At a higher pressure, the solubility of the gas increases, which supports Henry's law and the bends phenomenon. To wrap up the presentation, I'll leave you with another cool application of gas solubility in lake ecology. In lake ecology, there are 3 layers which are divided based on their different temperatures. These layers are referred to as the epilimnion, warm surface waters, the hypolimnion, cold bottom waters, which are separated by the metalimnion, or thermocline layer, a stratum of rapidly changing temperature. When warming temperatures alter the hypolimnion level to have higher than regular temperatures, the oxygen available at that level depletes and dissolves out of water. This affects the fish species, such as trout, which require cold water and dissolved oxygen levels, and they cannot survive after time. Thank you for watching this, and I hope you learned something new on the solubility of a gas in water.